Hey everyone, I think we've all noticed that there's a nice pattern with even and odd numbers that we can prove. For example, the sum of two odds is always even. The product of an even and an odd is always even. What's kind of amazing is we don't need to know which numbers we're adding and multiplying, just whether or not they're odd or even. It turns out that we can extend this technique much more broadly, and we'll be talking about that today and building on what we did in the last lecture. Let us review a few things from last time. Recall the definition of A divides B, or B is a multiple of A, the definition of A congruent to B modulo N, and finally the theorem that A is congruent to B modulo N if and only if N divides B minus A. These are all results from last time. Let's first get some corollaries from those results. So now let A be an integer and let N be a positive integer. Then there's a unique value R in the set 0, 1, 2 up to N minus 1 where A is congruent to R modulo N. To see this, notice that this is just the remainder from the division algorithm. We can also see that N divides A if and only if N is congruent to 0 modulo N. This follows directly from the theorem we proved last time. And what follows from that is that if N does not divide A, this is true if and only if N is congruent to any of the other numbers in that list, 1 through N minus 1. Now we can prove a theorem that is the basis of what we call modular arithmetic. Theorem: let N be a natural number and let A, B, C, and D be integers. Assume that A is congruent to B mod N and C is congruent to D mod N. Then, A plus C is congruent to B plus D mod N, A minus C is congruent to B minus D mod N, and A times C is congruent to B times D modulo N. Basically, what this is telling us is whenever you do arithmetic, you only have to pay attention to the remainders if you're doing things mod N. Also note, if we let N equals 2, this recovers all of those nice formulas we have for even and odd numbers that we've derived earlier in the class. So here's an example of how we can make this work for us. So we see that 12 is congruent to 2 modulo 5. So what is 12 squared modulo 5? Well, 12 squared is 12 times 12. 12 is 2 mod 5, therefore 12 times 12 is 2 times 2 mod 5 by the previous theorem. That's 4 mod 5. But we could check this directly, for example. 12 squared is 144, and we can see that that's 4 mod 5. But we can use this to get some really nice computations. For example, 12 to the 10th power is congruent to 2 to the 10th power modulo 5. Well, 2 to the 10th is 1024, and that's congruent to 4 modulo 5. Therefore, 12 to the 10th is congruent to 4 modulo 5. This one would be harder to check directly. In fact, 12 to the 10th actually turns out to be 61,917,364,224. And if we look at that, we can see that, look, it has a remainder of 4 when we divide by 5. But this is pretty hard to do by hand, and I'll admit that I used a computer for this. Okay, now let's prove this theorem. We're going to do the product formula, and the addition and subtraction will be quite similar. So let's assume that A is congruent to B mod N and C is congruent to D mod N. This means that N divides B minus A and N divides D minus C. That means B minus A is K times N and D minus C is L times N, where K and L are integers. Or we could write this as B equals Kn plus A and D equals Ln plus C. Now let's just compute BD. Plug in, use FOIL, and do a little bit of arithmetic, and we see that BD minus AC is a multiple of N, which again means that AC and BD are congruent modulo N. And that's it, that's the proof. Like I said, the addition and the subtractions are exactly the same. Okay, now here's a really hard example to do by hand. But here's a question. What are the last two digits of the number 99 raised to the 1,787,416th power? We could just compute that number directly and look at the last two digits. Good luck with that. But let's also observe that last two digits really just means remainder when we divide by 100, right? So what we're really asking is, what is 99 to the 1,787,416th power modulo 100? But also note that 99 is congruent to -1 mod 100. And we can see that because 99 minus 1 is 99 plus 1, which is 100, which is obviously a multiple of 100. Therefore, 99 to the k modulo 100 is -1 to the k modulo 100, which of course is either plus or minus 1, depending on whether or not k is even or odd. In this case, we chose an even k, therefore the last two digits are 0, 1. In fact, the previous argument tells us even more than that one particular computation. It tells us that the last two digits of 99 to the k should always be 0, 1 when k is even, and 99 whenever k is odd. Let me list a few of these powers here, and you can see that this pattern holds. Here's a trick that people maybe have seen before, but it's really useful, and I'm going to show you why it works. So here's the question. Consider the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, right? 1,234,567,890. Is this number divisible by 9? Now, we could just check by dividing in 9 and just seeing what we get and see if we get a remainder or not. But that's a bit of a mess. So I'll say, here's what we do. Don't do that. Do something else. Add up the digits. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 0. I'm just adding up the digits of this number, and I get 45. Okay? 4 plus 5 is 9. And I claim that since we got 9 by this process, the answer to the question is yes, 9 does divide it. So basically, here's the rule for divisibility by 9. Let n be any positive integer, and add up the digits of n. If you get a number with multiple digits, add its digits, and so on and so forth, until you get a single number. If that number is 9, then the original number is divisible by 9. If you get anything else, then it's not. Okay, so this is a neat trick, but how do we prove it works? The key observation to all of this is the fact that 10 is congruent to 1 modulo 9. And that implies that 10 to the k is congruent to 1 to the k modulo 9, but 1 to the k is just 1. Therefore, every power of 10 is 1 mod 9. So let's think about the number n in terms of its digit expansion. If the digits of n are given by ak minus 1, a2, a1, 0, then n, actually what that really means, n is ak 10 to the k plus ak minus 1, 10 to the k minus 1 plus plus a2 times 100 plus a1 times 10 plus a0 times 1. That's what it means when we write a number in decimal form. So let's take everything modulo n, remembering that all of the powers of 10 are 1 mod n. So when we take the mods, of course we can split up the sum, we can split up the products because of the theorem we had earlier, and it just becomes the sum of the digits. So what have we shown? We've shown that if you take any number in base 10 and you add up its digits, you get another number. Those two numbers have the same remainder when dividing by 9. Those two numbers are congruent mod 9. And of course, whether or not a number is congruent mod 9 is when you end up with a single digit, do you get 9 or do you get something else? Okay, one small warning. This trick is special to the number 9 and also to the number 3, but it is not generally applicable to check divisibility by other numbers. For example, you can't add up the digits and see if it's 0 mod 5, and that tells you whether or not the thing is divisible by 5. This only works for 3 and 9, okay? And the crucial idea here is that 10 is 1 mod 9, and it's also 1 mod 3. That's why it also works for 3, and it won't work for other numbers. I'll stop there.